Section 4.1 talks about real vector spaces. Now, there's real and there's complex. That depends on the scalar. The scalar is k. So if you choose k to be real, then we're talking about real vector spaces. And if you choose k to be complex, a plus bi, then we talk about complex vector spaces. For now, we're going to focus on real vector spaces. So also here. All right. Let V an arbitrary non-empty, so that's important right there. You want it to be a non-empty set of objects, right? And for which two operations are defined, addition and multiplication by a scalar. By addition, we mean a rule that associates each pair of objects U and V in V, and U and V are called the sum of U and V. And this is going to be defined in every problem. Every problem you get to, they're going to define in this vector space, addition is such and such, and scalar multiplication is such and such. Again, this will associate the scalar multiplied by U and V, and those differ. It's not a traditional addition or subtraction. Each vector space does specific addition and specific scalar multiplication. If the following axioms are satisfied by all objects, U, V, W, these are vectors in V, and K and M are scalars in real, we're talking about real for now, then we call V a vector space, and we call the objects in V vectors. Now, this is a lot to remember. We are going to show this in the beginning, but for the remaining subspace and span and bases, we want to focus on two main axioms, 1 and 7. For now, you're going to verify. They tell you pretty much what to verify, and then they say, hey, is this a vector space? You look at those and you figure out. If all of these you think hold, then you're fine. If they don't hold, you say, well, this is not a vector space because, and you could number them 1 through 10. Now, as far as the test is concerned, when we get to the test, I'll be more specific on how to do this. So we're going to start with the first example. Here it says, let V be the set of all ordered pairs of real numbers and consider the following. And for this vector space V, the addition, if you take those two vectors and add them, you take the I components of each and add 1 to it, and the J component of each and add 1 to it. And the scalar multiplication turns out to be identical to what we know. So just to practice, compute U plus V. So U plus V is 0, 4, plus 1, negative 3. Based on this rule, that will be, if you notice, you take the 0 plus 1 and add 1 to it. And you take the J, 4 minus 3, and you add 1 to it. And this extra 1 that's being added is right there. That's how this vector space set addition, and that will be a 2, what is that, 5, 2, 6. And the scalar multiplication is simple. If k equal 2, then when they say find ku, ku is simply 2 times 0, 4, and that's pretty much 0, 8, because here they define multiplication like our traditional multiplication. But their addition is slightly different. Their addition, they add a 1 every time to the components. Show that 0, 0 does not equal 0. Let's go to the actual work. Let's go to the actual, I think I have a step on that one. That's not a 6. That's a 4, 5. That's 2. Okay. Let's go and identify what the 0 is. The 0 in this case, so here they talk about, look, those two we're going to focus on. If you take U plus V, that's V plus U. The addition, you could pretty much switch the order anywhere you want. For 0 plus U equal U plus 0 equal U, that's what they denote as the 0 vector. So to them, if you take vector W and add it to U, and that is u plus w. And if that happened to be u, then that means according to axiom 4, w is the zero vector. So that's the part you really want to pay attention to. If you take u and add it to its opposite, you should get the zero vector as well. And if k is any scalar and u is any vector in V, ku is in V, that's really pretty much that expanded. And if you multiply k times m times u, you could pretty much multiply the constant times vector u, and 1 times any vector is itself. So if you take vector w and multiply it by u, and you get u, then in this case we say w is 1. And that's how things work. So in this case, show that 0, 0 is not 0. Well, let's see what that means. According to what we have, if we take 0, 0 and add it to u or v, it doesn't matter. So let's say in this case we add it to v1, v2. That would be, according to the rule, 0 plus v1 plus 1, 0 plus v2 plus 1, which is v1 plus 1, v2 plus 1. But that is not v1, v2, right? So therefore, 0, 0 is not the zero vector, not for the space. So for it to be the zero, first of all, right there, for it to be the zero in space, you must, again, by axiom 4, you must add both directions. You must take a vector plus u. You know what, I should have stuck with u there, all to u, not v. I should have used u right there, but it's the same thing. So if I want to go for C, if I take -1, -1, and add it to u, right? U is u1, u2. If I get u back, then that's the zero vector. That's how we define 0 in vector space. So isn't that -1 plus u1 plus 1? And that is -1 plus u2 plus 1. Again, the plus 1 is coming out of the addition right there. That's what the vector does. So what would that be? Wouldn't that be u1, u2, which is u? So I took this vector, called it w, and I added to u. And guess what? I got u. Now, if I do it the other way around, if I take u1, u2, which is u, plus this vector w, call it, which is -1, -1, what would happen? Wouldn't that be u1 plus 1 minus 1, u2 plus 1 minus 1? Wouldn't that be u1, u2? Isn't that simply u? So therefore, the zero vector in this case is -1, -1. That's what you add to any vector to get it back. So each vector has its own set of addition and scalar multiplication. Find two vector space axioms that fail to hold. We want to see what does not hold for this. Well, let's see. Multiplying by a constant normally, or addition. Addition, it worked. If I multiply by a constant, if I take k, u, according to the rule, again, this is the part that I should focus on. If I take k into u plus v, I should get ku plus kv, number 7. If I take k into u plus v, I should get ku plus kv. Well, that is going to be what? If I multiply it out, that's going to be ku1, ku2 plus kv1 plus kv2. According to the rule, that's going to be ku1 plus kv1 plus 1, ku2 plus kv2 plus 1. But we know that doesn't equal ku1 u2 plus kv1 v2, right? Because of the 1, that's not going to happen. So therefore, that one doesn't hold. And also if I take the constant, if I take the other constant. So either the addition or the constant you should really look for. Constant, if I look for number 8 or 9 actually, they both, but 8, the addition, 8. If I take two constant k plus m multiplied by u, I should get ku plus mu. If I take k plus m times u, that is k plus m u1, k plus m u2, and that's going to equal, according ku1 plus mu1, ku2 plus mu2, and if I take ku plus mu, so this is just the scalar multiplication, nothing more, same here. But if I take the addition of those, that is ku1, ku2 plus mu1, mu2. But if I use the addition, that's going to be ku1 plus ku plus mu1 plus 1, and that's going to be ku2 plus mu2 plus 1. And obviously those are not equal, so therefore k plus mu does not equal ku plus kv. Again, the addition and the scalar multiplication are not the same here, so this doesn't hold. If I look at the next problem, number 4, the set of all pairs of real numbers x0 with standard operation in R2. Well, axiom 1 says if you add the two, they should remain in there. Then u plus v equal v plus u. So in this case, again, it's a lot of steps. We're going to verify those. And we only have to do that for 2 problems. Well, axiom 1, if I take x0 plus y0, so u and v, or x and y, that would be x plus y0, which is in v for all real numbers, so that works. And if I take axiom 2, if I take x0 plus y0, that is x plus y0, which is y plus x0, which is y0 plus x0. So treat y and y as real numbers. Axiom 3, if we take x0, what was the third one? I forgot. Okay, so you're going to add this plus y0, z0 should equal x0 plus y plus z0, which is x plus y plus z0, and I could say that is x plus y0 plus z, again, vector addition, nothing more. Here we're not changing that in this vector space. We're doing standard operations, which is x plus y plus z. So that one holds. Well, if I want to be really picky, I should put this around those. Axiom 4, the one we just used, if you take 0 to be 0, 0, then you could take 0, 0 plus x0. That's x0, which is x0 plus 0, 0. We're supposed to work downwards, but to see them, I really want to put them straight. This is, of course, for only numbers x. What was 5? I forgot 5. 5 was, oh, u plus negative u equals 0. Okay, so if I take, for all real numbers, if I let u equal x0, then negative u will be negative x0. And if I take x0, which is u plus negative u. That would be 0, 0, which is, this is whether equal or do both. And if I take negative x0 plus x0, that will be 0, 0 as well. That checks. Axiom 6, if I take k multiplied by x0, that would be kx0, which is in V for all real numbers k and all vectors V. That's always going to be true because that's true in our traditional addition. Axiom 7. What does 7 say? 7 is the k plus m times u. Okay. If I take two constants, k and m, and multiply that by x0, that would be k plus m times x0, which is kx plus k plus mx, and that is kx0 plus km0, which is kx0 plus k. And that's for all values of m and k and x. 8. 8 was, oh, that was 8. 7, 7 was k into u plus v, my mistake. So here, we'll switch them. Call that 8. 7, k times x0 plus y0 is going to be k, and in this case the addition is x plus y0, and we could say that is kx plus ky0, and obviously that is kx0 plus, again by traditional addition, and that is k times x0 plus k times y0. So that holds. 9. I thought I left myself a lot of space. What does 9 say? If you take k times m times u, that's the same. Okay. So if I take k times mx0, well, we know what that is. That is k times mx0, and that is simply kmx0, but I could say that's also km properties of vectors, and that is true for all k and m being real. I haven't been writing that, and all x. I need a bit more space to show number 10 really quick. And number 10 was the identity, right? Yeah, 1 times u is u. And we know by traditional multiplication, 1 times x0 is simply x0 for all x. There, so a bit annoying to list all of those and verify. We have to do that on one problem. I'd like to look at number 7 next, and this is how really it's going to be. It's not going to be you have to memorize all of those. Focus on the 2 that I mentioned, or 3. Take 2 vectors in the vector space and add them, it should remain in there. Multiply by a constant, the ones I highlighted. Multiply by a constant, it should remain in there. Those are the 2 you should focus on more than anything, because that's what we're going to use for the rest. So number 7, the set of all triples triples of real numbers with the standard vector addition. So the traditional addition is the same, but the scalar multiplication, if you multiply by k, you square the k. Well, obviously, it's not going to hold if you take ky is going to hold, but if you take k plus, oops, wrong color. If I take k plus m times x or u or v, let's say in this case u, we expect that to be ku plus mu. That was that's the one I mixed up. So that was number 8 by 8. Well, let's see how this works. So if I take that, that's going to be k plus m squared x, k plus m squared y, and k plus m squared z. But we know that that equals to k squared plus 2km plus m squared x. And similarly, k squared plus 2km plus m squared y. And k squared plus 2km plus m squared z. But we know that if I take ku plus kv, that would be k squared and that'll be m squared x squared m squared, oh boy, m squared x, m squared y, m squared z, and that is k squared plus m squared x, k squared plus m squared z, and k squared plus m squared z. Oh, that's a y. And we know those are not equal. Therefore, axiom 8 doesn't hold. It's either the addition, most of the time, it's either the addition or the scalar multiplication. One more to go. The set of all 2 by 2 invertible matrices with a standard matrix addition. And okay, so the addition is the same as matrices. The scalar multiplication is the same. All 2 by 2 matrices invertible. So if I take 2 matrices, let's say I may take matrix A, which is, let me see, 1, 1, 2, 3. So if I take those, that determinant is 3. Okay, the determinant here is 3 minus 2, which is 1, not equal to 0. Very good. And if I take B to be negative 1, negative 1, 2, 3. And here the determinant would be negative 3 plus 2, which is negative 1, which doesn't equal 0. So those are also invertible. B is all. But if I take A plus B, wouldn't that be 0, 0, 0, 0? And the determinant, which means it is not invertible. So there's a counterexample. So this is not true under addition, and by that it's not a vector space. And that's pretty much it.